Hey everybody, welcome back. This is Pre-Calculus Day 8, and we're talking about combining functions. We want to add them, subtract them, multiply, divide, and then introduce a new idea called function composition. So let's actually say our goal. So yeah, basically we want to create new functions from old functions in a sense. So yeah, we want to create new functions from old functions. Okay, so let's see what we mean by this. So for example, so for each of these, let's let f of x equal x squared and g of x equal 3x. So this new function f plus g, this is exactly f of x plus g of x. I want you to be careful here because I know this might look like the distributive property. It's not. It's subtly saying if I want to compute this sum of functions, I do it in exactly this way. So there's no distributive property here, so be careful. So to compute this function, this map, the sum of functions, you just add these individually. So that'd be exactly what you want it to be, x squared plus 3x. And so we could take the difference of the functions. So this difference function or difference map is computed in the following way. So that's f of x minus g of x. And so that's exactly x squared minus 3x. So for 3, we could look at this product function or product map. And to compute this, it's exactly f of x times g of x. But that's exactly x squared times 3x, which is exactly 3x cubed. And then lastly here with this quotient function or quotient map, I need to be careful, right? I don't want to divide by 0. So to compute this, it's defined as f of x over g of x. Well, that's exactly x squared over 3x. And I want you to be careful here, so take notice. So yes, we can cancel these, and we will, but I still need to note that I can't divide by 0. So even though, again, these are going to cancel, I have to note that x cannot be 0. I mean, how on earth could these two objects be equal unless I note that? These are equal for all x's where I'm not dividing by 0. So we're going to note that carefully. So I might say, yeah, that's important even if you're canceling. So important even when canceling. So do be careful there. Okay, so let's define all these operations. So we're going to say let f and g be two functions and I'm going to say ideally, so the intersection of their domains is non-empty. I'll explain in a moment why that's important. So let's think about this. If I have two functions that have no common ground in their domain, then when I add the two functions, there's no way to keep that sum defined. I've got to have values in both of their domains in order for the sum to produce a meaningful output. Well, if that's the case, I'm going to say, well, then, for all x's that are in the domain of f, intersecting the domain of g, we define the following operations. And so 1, this special sum function or sum map is defined as follows. And we mentioned this before, so now we're just stating it formally in a definition. And so this is our sum rule. And again, before I go on, I want to just clarify this. This makes sense that their domains are non-empty. So imagine that this function has some domain that has nothing in common with this function's domain. If that happened, which we don't want to, but if that happened, then this entire sum wouldn't be defined because at least one of the parts would break, not have a meaningful output. So yeah, we have to have the domains of these two functions having something in common in order for this sum to produce a meaningful output. So you might want to pause and think about that, but it's very important. Just a matter of keeping functions defined. Okay, so this difference function or this difference map is defined exactly how you'd want it to be. So to compute this is to do this. Again, be careful. This is absolutely not the distributive property. This is how this difference function or difference map is defined. I know it looks like the distributive property, but this is not multiplication. This is us applying a function onto an input. Okay, so if I have this product function or product map, how do I compute it? How is it defined? Exactly as you'd want it to be, f of x times g of x. So that's the product function or product map. And then of course we could take the quotient function. So this quotient function f over g of x, again, is defined how you want it to be, or how you'd want it to be, like this, but I have to be careful not to divide by 0. So we always have to say that. So this cannot be 0 because this would not be meaningful if that were 0. And you have to be careful here. You might want to star this. So this is true even if this reduces. I still have to be very cautious of all the values before I reduce that would, cause a division by 0. So I'm going to say even if the f over g function reduces. So I still have to avoid these. So yeah, be careful there. Okay, so let's look at some examples. And this time, not only will we compute sums and differences, products and quotients, but we'll also compute some domains. Remember, we're always concerned with the domain of a function. We want to know which values keep the function defined. And remember, the domain of a function is the set of all inputs that keep the function defined. Sometimes I say it's the set of legal inputs. Okay, so let's say that f of x is equal to x, and g of x is equal to the square root of x. And let's say we want to find the following. So find the following. And how about we give the domain as well? Okay, so just as you'd imagine, let's say we want to find the sum function, the difference function, the product function, the quotient function, and we also want to find the domain. It might be nice to first note the individual domains. So maybe I'll say that. So I'll say first note. Okay, so this is f of x equals x, and so the domain of this would be the set of all real numbers. Every input keeps this function defined. For any real input I choose, I'll have a meaningful output. In fact, the same output in this case. So I'm going to say that the domain of f is equal to the open interval from minus infinity to infinity. Right? If I pick any input that lives inside of this interval, this set, that input will produce a meaningful output with this function. Now what about g of x? What's the domain here? So I'll say, and the domain of g, well, that would be the set of non-negative real numbers. And so we denote that in the following way in interval notation. So that's the domain of g. Okay, so now that's out of the way, we can find each of these and give their corresponding domains. Okay, so f plus g of x, remember how that's defined? So to compute that, that's exactly f of x plus g of x, but that's exactly x plus the square root of x. And so what would be the domain of this new sum function? Well, if I want to know which values keep this defined, I find the domain of each and then take the intersection. So I'll say that the domain of the f plus g function is exactly the domain of f intersecting the domain of g. That means what they have in common. But what do these two intervals have in common? Exactly this. Okay, so the difference, exactly as you'd imagine, that's f of x minus g of x. But that's exactly x minus the square root of x. Okay, and so the domain of f minus g, again, is the intersection of the two domains, f and g. And again, that's the interval from 0 to infinity, including 0. And so now we look at the product. So f times g of x, that's defined as f of x times g of x. That's exactly x times radical x. And then the domain is, again, the interval from 0 to infinity, including 0. And then let's take a look at the product. I'm sorry, the quotient. We just saw the product, so here's the quotient. So this is exactly f of x over g of x. And so here we have to be careful. So even if this reduces, we have to be careful. So we can't divide by 0, so there's no way I can include 0. And since that's a square root, again, even if we reduce, I can't input a negative. So the domain of f over g is the open interval 0 to infinity. Hopefully that makes sense, because again, I can't divide by 0, and I can't input any negative numbers here. Okay, so let's look at a couple more complicated functions. All right, so for example, let's say we have the following. So let's say f of x is equal to 2x over x plus 8. And let's say g of x is equal to, let's say, x cubed. And so again, let's find, maybe not all four, let's find the product function and the quotient function and their corresponding domains. And maybe just like before, let's maybe note the domain of f and the domain of g. So yeah, I'll say first note. Well, domain of f, well, of course we don't want to divide by 0. That's the only issue this could have, right? So for which choice of x do I divide by 0? Well, if x is minus 8, I divide by 0, so I want to avoid that. So again, the domain being the set of legal inputs, we're avoiding where we would divide by 0. And remember, in interval notation, that's how we omit a value. And so what's the domain of g? Well, all real numbers. I can plug any real number in here and cube it and expect a meaningful output. Okay, so we're ready to go now. So we want to go ahead and find the product function. So f times g, how do we evaluate that? Well, f of x times g of x. But that's exactly 2x over x plus 8 times x cubed. And that product is 2x to the 4th over x plus 8. And so what's our domain here? It looks like all real numbers except for 8. So the domain of our product function is exactly this. Okay, so let's take a look at our quotient function. So f over g of x. Remember to evaluate that, that's f of x over g of x. And so that's 2x over x plus 8 over x cubed. I'm going to write that as x cubed over 1. And I want to be careful because, so even if this is a compound fraction, I want to avoid dividing by 0. So as of right now, I need to exclude 0 because here 0 makes g of x 0. So that's out. So keep that in mind. So how do I evaluate this? Well, to divide by a fraction means to multiply by the reciprocal or flip. So one of those will cancel. That'll leave me with 2 over x squared, right? If I cancel one of those, x squared's left over, times x plus 8. And so again, for emphasis, I'm going to say we want g to be non-zero. So that's telling me to avoid 0 and also avoid minus 8. So the domain of our quotient function looks like this. So we avoid minus 8. and we also avoid, looks like 0. So there is our domain. Okay, so the whole goal so far is to create new functions from old ones with our operations, right? So we've added functions to create new functions, we've subtracted functions to create new functions, we've multiplied functions to create new functions, and we've divided functions to create new functions. Well, I want to introduce a new operation that's unique to functions. So with the first 4, these are all operations that you could do with numbers. You can add and subtract and multiply and divide. But with this 5th operation, again, this is going to be something special and unique to functions, and actually very, very important. So I might star this. It's very, very, very important. I really can't stress that enough. This is the composition of functions. And maybe before I define it, I want to have you realize that you've done something like this before. When you're in geometry class and maybe you perform a rotation of a figure and then a slide of that figure, that's the composition of functions. You're doing like a sequence of steps or a sequence of functions. So if you do a reflection and then a dilation, and then maybe you do a translation, that's a composition of functions. You're doing like a sequence of functions, a function after a function after a function. So yeah, so if I take my pen, let's say I rotate it, and then I translate it, that's a composition of functions, a sequence of functions, a function after a function. Okay, let's define that formally though. So we're going to say, suppose f and g are 2 functions. The composition of f with g denoted in the following way. This little bubble is our composition operation, is defined in the following way. So the composition of f with g of x is defined as exactly this. And that's provided x is an element of the domain of g, and g of x is an element in the domain of f. Okay, so what does this look like in a diagram? So let's say I've got some set here. Let's say I've maybe got some other set here, and maybe I've got some other set here. And so I'm going to start with some element x. And then what I want to do is, say I want to send x over here via some function g. So if I take x and I apply the function g to x, the result is whatever output I get from g of x. So the image of this, so the after effect of applying g is this. I get sent over here to g of x. That's, again, the output I get after I apply the function or map g. So see what I mean? So x is in the domain of g. And then, so let's say I take this output and I want to apply another function. See what I mean by like a sequence of functions? So if I take this, I can apply another function. Let's call that function f. And maybe I land at this little element over here. Maybe that's so that's after I apply f. But what did I apply f to? I applied f to g of x. So this is the image of this after I apply this function. So this function takes this, applies a rule to it, and you land here, this output, f of g of x. Okay, so you take an element, apply a function, the output lands here. You take that output, and then you now let that be the input of this function. This function takes this, and it lands somewhere over here. Okay, so input, there. This is the output of this, which now becomes the input of this, and this function takes this, brings it over here. So this sequence of functions or maps, 1, 2, could happen all in one swoop, and that's the composition function. Does it all at once. Sometimes, and often when I think about this, I read this as f after g. When I was in high school, I was trained to read this as, I think, f of g. But I think it's more illuminating if you say f after g, because you apply the g map first and then the f map. That way you never get confused with the order. So f after g. Okay, so you apply the g function first and then f after g. So yeah, when it's written like this, I'll often say f after g. And so when it's written like this, I'll often say f of g of x. So be careful. Apply this function onto this input. Okay, so I hope you see what I mean by a sequence of functions. So take an input, apply this. Here's your output, but it's now the input of this. Apply this, you land here. But how could I have done that in one single function? That's what the composition does. It takes like this whole sequence of functions and says, so I can bring you from here to here via this single function here. Sometimes you'll see a diagram that looks like this, like a triangle. Start with some function g. Then apply f. So if I want to land here, do you see how it's f after g? G first, then f. So to go from here to here, function 1, then function 2. But I could do that all in one swoop by applying f after g. That little diagram sort of sums this up. Okay, so let's start to play around with this idea, because as I mentioned before, it's incredibly important and it never stops being important, whether it's pure or applied math. Okay, so for example, let's say that f of x is equal to 3x squared plus 1 And let's say that g of x is equal to maybe x minus 4. Let's compute the following. So we want the composition map at, let's say, 1. And then let's say we want this composition map, so g after f, at minus 2. And then let's find general functions for both composition maps. So f after g of x, and then the composition map g after f of x. Okay, so what do we mean? So we want this f after g map applied at 1. So that's exactly f of g of 1. So what does that mean? It means I'm going to feed 1 to the function g. So 1 will be the input of g. And whatever output I get from g, that output becomes the input of f. So I'm applying now a sequence of functions or a sequence of maps. I apply g first, get an output, and then I apply f to g's output. Okay, so step 1 is to compute g of 1. So g of 1, and I'll write this in steps so you can clearly see. So to find g of 1 means that I plug 1 in for x here. So that'll be my inside here. So that'll be 1 minus 4. But that's exactly f of minus 3. So as you can see, the output of g is now the input of f. I'm applying f after g. So now I go to the f function, and I evaluate it at minus 3. And so that's 3 times 9 plus 1. So that's 28. Okay, so let's now evaluate this. So for 2. G after f evaluated at minus 2. That's exactly g of f of minus 2. So how do I interpret this? Minus 2 is the input of f. Apply the f function. Whatever output that gives you becomes the input of g. So g after f. Okay, so again, so go to the f function, plug in minus 2, so this will be g of 3 times minus 2 squared plus 1. Clean that up. As you can see, that's the output of f, which becomes the input of g. So let's see here, what do we have? So this is going to be 4 times 3, which is 12, plus 1 is 13. And so now 13 is the input of g. So go to g, and input 13 for x. So that gives me 9. Okay, so I think we're going to do part 3 on the next page, and just for quick reference, I'm going to write f and g again, if you don't mind. And so, yeah, let's just note, we said that f of x was 3x squared plus 1, and g of x was x minus 4. So 3, we wanted a general expression for f after g. Again, you'll often hear f of g, but again, I think after is more descriptive. So this is f of g of x, or f after g of x. So what does that mean? It means that I plug g of x in for f. So g of x is exactly this. So everywhere that f has a variable, you're going to plug in x minus 4. So you go to the f function, and everywhere that you see a variable x, you're going to substitute in x minus 4. So it's like we're plugging a function in. Okay. So this is 3 times x minus 4 squared plus 1. Did you see that? So I went to f, and I noticed, oh, f has an x right here. This gets substituted in for that x. And now I'm going to multiply this out. So let's recall the following. I've used this, I think, a couple times so far in this course, but I'm going to continue to use this. So a plus b quantity squared is a squared plus 2ab plus b squared. So let's use that right here. So that's going to give me x squared minus 8x plus 16 plus 1. So you can see a squared, double the product of the inside, and then minus 4 squared. Okay, let's go ahead and distribute the 3. If I distribute the 3, I get the following. So it looks like I get 3x squared minus 24x plus 48 plus 1, just combine like terms. Okay, so what does this do for me right now? Just keep in mind the definition. Okay, so it's f after g, so the g map is applied first. So after I apply g to the input x, I land at some value, some output, g of x. Okay, then I apply f. And I land here at f of g of x. Okay, so that's like all the process we went through. And what is this? This is like going from here to here all in one formula. So this is actually saying how to go from this input all the way over here. So that is f after g. Okay. So instead of going these little bunny hops, these little sequence steps one by one, this will have us go from here to the end in some sense. Okay, so for 4, we want the reverse map. We want g after f. I think I'm going to keep this part up. And then let's go ahead and do 4. Yeah, let's do it like this. So here's 4. So g after f of x, that's exactly g of f of x. Or sometimes we would say g composed with f of x. So actually, maybe I will change. I'll hide the diagram because this diagram is for the reverse mapping, right? So sorry, diagram. There we go. That's what we need there. Look at that. Okay. So what do we want? We want g of f. So we're going to go to g, and everywhere that g has a variable x, we're going to plug in 3x squared plus 1. So in for that x, we'll go this quantity. So x minus 4, it's just that's our x. But this is just combining like terms, so that's 3x squared minus 3. So what's happening in this case? So what's happening in this case is you start with x and you apply the map f first, right? So start with x, apply the map f first. You're going to land at some value, f of x, and then you apply the map g after f. and maybe you land here via the map G, but that's going to be G of f of x. Well, instead of doing this step by step by step in these little bunny hop sequences, how could I have done this all at once? Well, via the composition map, and that's what that formula is telling you. G after f. But what do we notice? Look at this. G after f. Here's the formula for G after f. Is that the same as f after G? F after G was this. So G after f is this. F after G is this. They're not equal. In fact, in general, they're not equal. So let's note that. That's actually an important property of this composition. So in general, f after G is not the same thing as G after f. What do we mean by in general? It's like saying it's not always true. It doesn't mean there aren't a couple exceptions, but in general, when I say they're not equal, it means they're not 100% of the time equal. So you have to be careful there. So I'm actually going to say this means they're not always equal. We're actually going to notice in the next section some very, very important and special cases where they are equal. But to say something like this in math means it's not always the case that they're equal. So this not equal to this means it's not always the case that they're equal. Okay, so I think it's important now to start bringing in domains. This will be very, very subtle, a little finicky, but absolutely worth it. So in this case, let's let f of x equal x over 2x plus 1 and g of x equal 2x plus 1 over x. Let's first compute g after f of x and find its domain. Okay, so let's first note something. So g after f of x is g of f of x. But that means that I need to take the function f, and that's going in here. So the function f is x over 2x plus 1. And everywhere that g has a variable, here and here, so everywhere that g has a variable, I need to place in a copy of this. Okay, so in for x here and x here, you're going to see a copy of this entire expression. So this will be 2 times the expression plus 1 over a copy of the expression. So you can see no matter how intense this looks, or no matter how many terms there are, or no matter how large or small this is, everywhere that this function has an x, this is going to get input for that x. Okay, so here and here. Okay, so that takes care of that. And then downstairs, same deal. Okay, so let's clean this up. So to clean this up, we're going to multiply by, oh, there should be a 1 there. We're going to multiply by we're not so thrilled with these compound fractions, right? These fractions within fractions. So to tame that, let's multiply by 2x plus 1 over itself. Perfectly legal, we're just multiplying by 1, but it's a useful form of 1 that's going to turn this from a compound or a complex fraction to just a fraction. So imagine distributing, right? There's two terms here, 1, 2. So if I distribute, think about what cancels and what stays. Now here, the 2x plus 1, those are going to cancel. That's going to leave me with 2x. Okay, so cancel for the first term, so 2x. And then here, that's going to be 2x plus 1, right? If I multiply anything by 1, get the other thing. Now downstairs, this is nice because this and this will cancel. That's going to be over x. And then up top, I've got 4x plus 1 over x. Here's where I need to be super, super careful. So let's note a couple things. I want to note something about the original function that we started with. So the domain of this and the domain of this little piece, and then I can give the overall proper domain. So let's think about this. For this function here, are there any values or any choices of x that are not in its domain? I mean, if x is equal to blank, this function's not defined. Right, so, well, what you can do is you can set that equal to 0, the denominator, and then you want to avoid that. Because exactly this value creates a division by 0. So think about this, right? This minus 1/2 is not in the domain of this function. So as we pass through the sequence of functions via composition, this never gets used in a sense, right? Because if it's not in the domain of the original, then it's not going to get sent. So I need to avoid this. The next thing I need to look at is this, the domain of this. So I've got one value to avoid from the starting input function here, from its domain. And then I need to also look here. So what value do I also want to avoid? X equals 0. So this first value created a division by 0 here, which we can't have. And then here, x equals 0 creates a division by 0 here, which we can't have. So I have to look at this, and then what we end up with. Those are two things. Essentially, in some sense, you're taking the intersection of their two domains. But see if there's any values that are illegal from the first function, and then the ending function. We're going to avoid them. So then I can say that the domain of g after f is exactly minus infinity to minus 1/2, union minus 1/2 to 0, union 0 to infinity. So another way to do this, as some people do, is the following. So some people do this. So they say, so that was our starting input function. And they'll say, okay, well, the domain of f is exactly this, right? Because you don't want to divide by 0. And then they'll say, once they get to the ending function, they'll say, let r of x equal this function here. So this function by itself, almost ignoring the sequence of steps that generated it, but imagine it's all by itself. And so the domain of R is equal to, well, avoid dividing by 0. And then the domain of G after F is equal to the intersection, what they both have in common. So the domain of F intersecting the domain of R. That's actually a good way to do this. So what do these two sets have in common? If you're unsure, just draw a little diagram. So suppose someone's unsure. They could say, okay, well, here's minus 1/2 and here's 0. And we want to avoid both of them. And so the first set looks like this. The second set looks like this. Right, this filled in, and then this. And then their intersection, what they would have in common would be this. This, union this, union this. Okay, if that's unclear, you can stack them. So the first one, you can say, okay, domain of F looks like this. The second one, you can say, okay, the domain of R looks like this. And then look at the two pictures. What's their intersection? Exactly where they share shading. So their intersection would be this, union this, union this. That's another way to do this. And it makes sense because if I follow, an element all the way through it, it has to be defined in order to get to the last function. So, or I've got to have elements that keep the functions defined. So if x is minus 1/2, that's not good because my starting function says that's not in the domain. So that's not getting sent anywhere because it's not even in the starting function. This is not even in the ending function, right? So that's gone. So this, right from the start, couldn't get sent anywhere. It's like broken right off the bat, so I want to avoid it. And then at the end, I notice that this breaks this function. So combining both ideas, I get the following domain. I think that was a bit of overkill, but I think it was worth it. Like the good kind of overkill. Okay, so let's look at the opposite composition. Let's look at F after G. So this was G after F. Let's do F after G. So F after G, that's exactly F of G of X. But let's recall, if you don't mind. So G of X, we said, I think was 2x plus 1 over X. And then F of X, we said, was X over 2x plus 1. So it looks like they're reciprocals of each other. Not inverses, but reciprocals. Okay, so how do I compute this? I need F of, well, G of X is 2x plus 1 over X. What does that mean? Well, algebraically, I go to F, and everywhere that F has a variable X, namely here and here, I replace it with a copy of this. Okay, so I'm going to see a copy of this right here, and I'm going to see a copy of this right here. So that's going to be 2x plus 1 over X. That entire chunk went in for X over 2 times 2x plus 1 over X plus 1. So remember, the first thing we want to look out for is, are there any values, any choices of X that would make G undefined? Well, if X is 0, G is undefined. So we want to avoid X equals 0. So notice I'm starting with the inner function and saying what's its domain. So I want to avoid. So that means that the domain of G is minus infinity to 0 union 0 to infinity. Okay, so now let's do some more algebra on this, and then we might play that let R of x game and then find the intersection. Okay, so to compute this algebra, let's multiply the top and the bottom by x. X over 1 over x over 1. That's going to get rid of the complex fractions. Think about the canceling. And so the numerator is going to be 2x plus 1 because both of these x's will cancel. Downstairs, so this needs to get distributed to both, right? So here, these x's will cancel. That's going to give me 2 times 2x plus 1, and then 1 times x is x. But this is exactly 2x plus 1 over, that's going to be, looks like 4x plus x is 5x plus 2. So that's going to be the function I say let R of x equal. So let R of x equal 2x plus 1 over 5x plus 2. Are there any choices of x that would make this function undefined? Well, if you set the denominator equal to 0 and solve it algebraically, you'll see that if x is minus 2/5, that will be undefined. So we want to avoid that. So avoid x equals minus 2/5, again, because it makes the denominator undefined. And now for the overall domain. So the domain of f after g is exactly the domain of g, the starting inside function, intersecting with the domain of R. Remember, intersection looks for what's in common between the two sets. So what is the domain of R, by the way? I should probably write that down. So domain of R, minus infinity to minus 2/5, union minus 2/5 to infinity. So what do these two sets have in common? This set and this set. Well, the open interval from minus infinity to minus 2/5, union minus 2/5 to 0, union 0 to infinity. There we go. So that's what I mean by finicky, right? So you have to be careful of the domain of the inside function, the domain of what you end with. It makes sense to call this R of x because looking at this by itself, it sort of ignores the sequence of steps to get there. So I treat that individually, I treat that individually, what's their domains, then take the intersection. Okay, let's do an interesting one. Let's look at f composed with itself. In certain situations, one thing that we do in mathematics, particularly in applied mathematics, is that we'll take a function, we'll compose it with itself a lot of times, essentially. So, for example, like, take cosine and compose it with itself. So take cosine of cosine of cosine of cosine of cosine of cosine of cosine. And we look for certain solutions, and these are called fixed points, and they give us a lot of important insight into both the function and what it's modeling. So you don't have to know all of that now, but you should realize that this composition, that's one reason of many that it's important, is that it can give us insight into some functions. But there's a whole slew of reasons it's important. Okay, so for 3, let's just recall that f of x was x over 2x plus 1. Let's find f after f of x. What does that mean? It's f of x. So what does that mean? It means that I need to plug in a copy of f everywhere that f has a variable x. So that means I'm going to plug in an entire copy of f here and here. So that's going to give me, so in for this goes an entire copy, and then in for this goes an entire copy of f. We can do algebra in the typical way. So getting rid of these complex fractions, I'm going to multiply the top and the bottom by 2x plus 1 over 1 over 2x plus 1 over 1. Multiplying, that's going to help us get rid of the compound fractions. So these will cancel. I've got an x here. And then remember, this is going to get distributed here and here. So this will cancel. I get a 2x here. And then 1 times this will be 2x plus 1. So that's going to give me x over 4x plus 1. And there's two things I want to know. So I want the domain of f. Okay, so are there any choices of x that would cause this function to be undefined? If x is minus 1/2, the function is undefined. So we want to avoid minus 1/2. And then remember, we're going to play the game. Let r of x equal this final function here. And so what's the domain of r? Well, we want to avoid any choices of x that would make the function undefined. So minus 1/4 does that, so we want to avoid minus 1/4. Again, if you wanted to solve for that algebraically, you just take the denominator and set it equal to 0. Okay, so how do I find the proper domain of f of f? It's the intersection of these two domains. So I'll say that. So the domain of f or f after f is exactly the domain of f intersecting the domain of r. But what do these two sets have in common? Well, what do they have in common? Everything except for minus 1/2 and minus 1/4. So that's minus infinity to minus 1/2. Union minus 1/2 to minus 1/4. Union minus 1/4 to positive infinity.